And we were still on applications of functions. So we're learning everything about functions. So let's go ahead and finish these up. Okay. Number 6. In meteorology, where's my pen? Dun, dun, dun. I can't do much if I don't have my pen. Oh, I wonder if my daughter hid it from me. Oh, no, found it. Cool. All right. So in meteorology, the temperature is related to the altitude by the formula T of H equals negative 3.5 H plus 58.6, where H is in thousands of feet and T is the temperature in degrees Fahrenheit. A, identify and interpret the slope. Okay, so looking at this equation, what do you think the slope is?
Isn't it negative 3.5? I think.
Good. Slope is negative 3.5. And I'll put the H on there, right? So slope is negative 3.5 H. Well, what does the slope mean in this problem? So it says temperature is related to the altitude, and H is in thousands of feet, and T is the temperature in degrees. So if H is in thousands of feet, so as you climb higher and higher and higher, what's going to happen to your temperature?
It's going to decrease.
It's going to decrease. And that makes sense because our slope is also negative. So if you have a negative slope, this means as we get higher in the altitude, the temperature is going to decrease. So that's what our slope means. So we can say as H increases, temperature, T, right? Temperature will decrease. Okay. And then B, what should be the temperature if the height is 12,000 feet? So here they're giving us the altitude, which is H. And now for B, all we have to do now is plug in 12 for H, because we're not going to plug in 12,000 because remember, H is already in thousands of feet. So we're just going to plug in 12. So for B, we are going to say T of 12 is equal to negative 3.5 times 12 plus 58.6. And what would the temperature be at 12,000 feet? Who's got it?
$100.6.
I got.
What you
Wait, you
get?
said I got 16.6.
There you go. 16.6. 16.6 degrees. So check your calculations again. But yeah, 16.6 degrees. Okay. And then C says, at what height will the temperature be 32 degrees? So now they're giving us temperature and we have to solve for the height. So in C, they're giving us the temperature, T of H is equal to 32 degrees. So that means we take 32 and plug it in for T of H. So we will have 32 equal to negative 3.5 H plus 58.6. And now we are going to solve for H. So subtract 58.6 to the left side. And say minus 58.6 minus 58.6 and 32 minus 58.6. What is that?
26.6.
26.6, but negative, right?
Yeah.
Negative 26.6 equal to negative 3.5 H. And then we will just divide by what to solve for H?
Negative 3.5.
Negative 3.5. So you'd have negative 26.6 over negative 3.5 equal to H. And what does that give me?
7.6.
7.6. Good. But remember, height is in the what?
Thousands of feet.
Thousands of feet. So to get our actual answer, we have to take 7.6 and multiply it by what?
1,000.
1,000. And 7.6 times 1,000 is how many feet?
7,600.
7,600 feet. Okay. So at 7,600 feet, the temperature is 32 degrees. Okay. That one wasn't bad. Okay. Everybody good with that one? Thumbs, got some thumbs. All right, perfect. Who's alive out there? Okay. Now, number 7. In 1990, Americans ate out at a restaurant an average of 143 times. By the year 2000, this had reached 170 meals out a year. If there is constant growth, how many meals a year do you expect us to eat out in 2030, in the year 2030? Okay. So in order to figure that out, well, we have to figure out the constant growth. How much are people eating at restaurants every year? So what they're actually giving us is 2 points. So if we write this down, the first point is that in 1990, Americans ate 143 meals, an average 143 meals at restaurants. And then in 2000, they ate an average of 170 meals. Well, we've seen this before. If you're given 2 points, what can you find between 2 points?
The slope?
Slope.
Question mark.
Good. Yes. So if you're ever given 2 points, you can find slope. So that's what we're going to do. Here's my x1. There's my y1. Here's my x2. There's my y2. And my slope that will represent the constant growth of average meals per year will be given by y2 minus y1 over x2 minus x1. And 170 minus 143, that's what? 27. And 2000 minus 1990, that's 10. And what is 27 divided by 10?
2.7.
2.7. Okay, so there's our slope. So from 1990, so what we're saying is that right now, from 1990 to the year 2000, there has been a constant growth of Americans eating at restaurants an average of 2.7 times each one of those years. Okay, so that is the average growth. Now, what we want to know is how many times will we eat at a restaurant in the year 2030? So, what do you think we do with that information? Nothing. Okay. Well, if our data started off in 1990, how many years is 2030 from 1990?
40 years.
40 years. Good. And if the constant growth is 2.7 meals per year, then what should we do with that?
Multiply it.
Multiply it. Good. So we know that 2030 minus 1990 is a difference of 40 years. Now take 40 years and multiply it by 2.7. What do you get?
108.
108. Okay. But we're looking for total. So we already know that we're going to eat 143 times because that's what 1990 told us. But now you're going to take that 143 and add it to what?
108.
108. So in the year 2030, we are expected to eat at restaurants an average of how many times? What is 108 plus 143?
250.
251. There you go. That's how many meals we will average at restaurants in the year 2030. I mean, I might average that at Bill Miller. I love Bill Miller just for no reason. There's nothing amazing about Bill Miller other than that I love it.
Their brisket tacos are amazing.
Their breakfast is good, but I mean, everybody's like, ew, why? I'm like, look, it's fast food barbecue, and it's the best fast food barbecue you're ever gonna get. Yes, you can go wait in line for hours for amazing barbecue. I've done it, but Bill Miller, my goodness, if you need something quick and on the spot, that does the job. So there you go. I love Bill Miller.
Agreed.
Okay, so 251 meals, average meals in the year 2030. Okay. Number 8. Give an example of a real life situation with a variable cost and a fixed cost. Ooh. So remember that when you're talking about a cost function, it's C of X or Y equals a variable cost plus a fixed cost. Now, what do you think what real life example could be put into a cost function? something that is variable cost and a fixed cost. And you could even think back on the other problems we worked.
Would gasoline maybe be one?
Gasoline would be one, so good. Let's say maintenance on a car, right? Car maintenance. Car maintenance. I'm probably not spelling that right, but whatever. So let's say our car maintenance, we know the cost would be gas. So gas would be your variable cost because it's like $2.50 per gallon. It's an amount per gallon, right? So gas would be times X plus, what do you think your fixed cost? So if we're thinking car maintenance here, so your fixed cost would be what? What do you have to do to keep your car running other than fill it with gas?
Oil change,
Oil change. What else?
tires.
Tires, air filter, everything, right? So that would be your fixed cost throughout the year. Yes, you get gas, but in order to keep it running, you rotate the tires, you get an oil change, you change out your air filter, you do all that good stuff. So gas plus, we'll say mechanical. That would be a real life cost function for anybody. So gas would just be variable. You know you have to get gas and it's always X amount per how many gallons. And the mechanical, tires, oil, anything like that. Okay, cool. That's good enough for me. And of course, I mean, other real life examples would be if you had your own business. How much does it cost you to make a product? And then how much are the materials? So it's say you make t-shirts. It costs you $5 per t-shirt, but then the materials, the print, the whatever else you have, the packaging, that would be a fixed cost. So those are all real life examples of a cost function. Okay. Number 9, a bacteria population doubles every minute. Explain why this population growth cannot be modeled by using a linear equation. So think about it. So if bacteria doubles every minute, that changes from linear to what? Let's say I had a population of 2, then it doubled to 4, then that doubles to 8, then that doubles to 16. Could you model that by an actual linear equation?
I don't think so.
No, why don't you think so?
Because wouldn't you have to like square it or something like that?
Good, good. And the name for that is called exponential. So if bacteria is doubling every minute, it becomes an exponential equation. And you would have to represent it. And since this is doubling every 2, it would be represented by 2 to the x power, 2 squared, 2 cubed, 2 to the 4th. So that's how you would have to represent it. And one way to put it into easier terms, if you look at number 7, remember slope is constant. Slope doesn't change. On number 7, slope was 2.7. We were eating an average of 2.7 meals out at restaurants every year. So what slope does, slope is constant. If bacteria is doubling, then that is exponential. So that is why we cannot model it by a linear equation. Okay. So everybody go with that? Okay. And last one. Oh boy. How much water should be, oh, they threw in a mixtures problem. My goodness. It's like, hey, remember this? How much water should be added to 1 quart of 3% milk to result in a 2% solution? How many quarts of 2% solution would this make? Okay. So this is like a refresher from the first test. Nothing crazy. So we have milk, water, and total solution. Okay. And then the amount of each one. And in milk, we are adding 1 quart. And then the percent of that milk is 3%. So 0.03. And then remember the last column is amount times percent. So 1 times 0.03 is 0.03. Okay. And then it says, how much water should be added to 1 quart of milk to result in a 2% solution? So we don't know how much water we need. We know that water is a 0% solution, and x times 0 is 0. And then down here, you would have 1 plus x. And we want a total of 2% in our solution. So that will be down here, 0.02. And 1 plus x times 0.02 is 0.02 times 1 plus x. Okay. Now put it all together and you will get 0.03 equal to 0.02 times 1 plus x. All right. And now solve for x. So the first thing we're going to do is, what could we do? We can we'll distribute. Let's do that. That'll be easier to look at. 0.02 times 1 is 0.02 plus 0.02x. And then subtract that to the left side. That's going to be 3 cents minus 2 cents, which gives me what?
1 cent.
1 cent equal to 0.02x. Then you will divide by 0.02. And 0.01 over 0.02 leaves me with what?
Point 5.
0.5. So you get 0.5 equals x. Okay. So we would need to add half a quart of water in order to make the 2% solution. And you would make 1.5 total quarts of solution. So we put that 0.5 quarts of milk and 1.5 quarts total solution. Okay, cool. And that is applications of functions, which means that those notes are done, which means we're done. So let me stop recording here.